All right, the warm-up question for today asks you to read the triboelectric series that you see on my screen. It says, a neutral steel rod is rubbed with a nylon rag, which will lose electrons, and then which will have a greater magnitude of charge after. So this is another triboelectric series similar to the one that was on the screen yesterday, but this one's got a little bit less detail, fewer materials on it. You'll see and saw different ones in the problem sets previously. Some of them have a lot of stuff on them. Some of them are shorter like this. But you should still be able to read them in the exact same way. So if you were to rub steel and nylon, you'll find nylon up here toward the top of the list, and then steel is beneath it toward the bottom of the list. The question, though, isn't which is positive or which is negative, but instead which will lose electrons. So you need to think to yourself, if it loses electrons, what charge will it obtain? And if you lose electrons, then you will have a positive charge. So the question is really asking which one will become positive, but it's saying it in a way that makes you have that extra step in your thought process. The positive one is whichever one's higher. Okay, so the higher on the list is the nylon. So the nylon would become positively charged, meaning that it would lose its electrons. That's the answer to number 1. Number 2 says which will have a greater magnitude of charge after. Well, guys, if they start out both of them neutral, that means that they both have the same number of protons and electrons initially. And so all that's happening here is that some of the electrons are transferring, specifically transferring away from the nylon and into the steel. But it's the same number. And so let's say the nylon loses 13 electrons. Well, then the steel has gained 13 electrons. Okay, you have to conservation of mass, conservation of matter, whatever. You're not creating or destroying new electrons. You're just transferring them. And so if one of them loses 13 and the other gains 13, and really it's going to be a much bigger number than that, but you're going to have the exact same magnitude of charge. One of them is going to be positive, one's going to be negative, but the amount of charge that each will carry will be the same. So the answer to number 2 is they will have the exact same magnitude of charge. Opposite signs, but same magnitude. Okay, so please make sure you have answered the warm-up questions for today. Does anybody have a question about today's warm-up? All right, then again, make sure you've answered that. And as I said, we're going to finish our notes today with transfer of charge. We only have one type of interaction to talk about still. And then your problem set today will go over that. That's going to be charging by induction. But it will also include everything else from the unit. Think of it as kind of a review. So let's go ahead and get into our notes. So electrostatic induction is the process in which redistribution of charge takes place within a body when an electrically charged body is brought near it without touching. It's a really kind of wordy way of saying that, hey, if you bring a charged object near some other object, it's going to cause the electrons in the object to move due to the charge. And we see it here. This was one of the animations that you saw in the simulations, comparing specifically a conductor versus an insulator. But you see a similar type of behavior. It doesn't look the same because the properties of those materials are very different. But in my conductor, when I bring this positively charged body nearby, opposites attract. The electrons, since they flow freely, flow to the left-hand side of that material, and now I have a concentration of electrons on the left and a lack of electrons on the right, and I've caused something called polarization, which we'll have on the next slide as well. Okay, in the insulator, rather than the electrons moving freely, they are kind of locked up in those orbits because an insulator doesn't allow the free flow of electrons. It's going to be something like a rubber or plastic or something like that. They can't flow through it, but they can still have polarization because it can cause the distortion of the electron orbitals. So they're still in orbit around their respective nuclei, but now the orbitals are kind of skewed to one side. And in this case, again, opposites attract, and so you can still see those negative electrons spending more time toward the left-hand side of the material, toward that positively charged object. And this all happens even though nothing touches. Yesterday, charging by friction, you had to have two objects touching, specifically rubbing against each other. Yesterday, in charging by conduction, we had to have two objects touch so that the charges could transfer. And in this case, there's no contact. Okay, and it's just causing the separation of charge. And that's actually the first step in charging by induction, is causing polarization, which is what we just saw on the last slide as well. But polarization is the process of separating opposite charges in an object, leaving you with a positive side and a negative side, leaving you with poles, a positive pole and a negative pole. And so that's what you see in this animation, is you end up with this polarization. Now it's temporary because you move the charged object away, it goes right back to normal. Okay, but you can use polarization to create a charge in a material as well, which we'll look at in a second. But it's the first step. You can also see polarization here. This was one of the animations when we did charging by friction, where we rubbed the balloon on the boy's hair. But the polarization actually occurs when the balloon sticks to the wall afterward, because the charges in the wall behave the same as the charges in the insulator here. You get this polarization, and the balloon will actually stick to the wall. You could try it on your own. It may or may not work very well with the humidity that we have here, but you can try it. It is something that should work, especially on a dry day. It will work. And you can actually cause a balloon to stick to the wall if you charge it up first by rubbing it on your hair or on a wool sweater or something like that. All right. So again, this is polarization, where you separate those charges, leaving a positive and a negative pole or side to your material. However, in these cases, in both cases, the overall charge is still neutral, because I haven't allowed electrons to transfer. When I bring the positive rod nearby, it does cause separation, but I still have the same number of protons and the same number of electrons, because there's no pathway for them to leave. Okay. When I have the polarization here, again, those aren't going to flow out anyway, but there's still no pathway for them to leave. And so both of the materials are currently still neutral. Same thing with the wall. It's still neutral. We just see this polarization that causes the same opposites attract, and then the balloon sticks to the wall. But again, you can induce a charge using polarization. It just takes some extra steps. So let's talk about electrostatic induction. So here we have charges in two different materials, a wooden rod, which is on the left, and a steel nail, which is on the right. And notice that each of them has an equal number of protons and electrons, meaning that both of these things are neutral. Nothing has a charge, they're just hanging out. But if you were to bring them next to a Van de Graaff generator, like the one that we had in class last week, that Van de Graaff generates a negative charge, and if you bring them nearby, the charges in the wooden rod aren't going to do anything, okay, if it's just sitting nearby, because they can't flow. Wood is an insulator. But the charges in the nail can flow. And if you look at the nail, those negative charges, because the Van de Graaff is negative, and because like charges repel, and because it's a conductor, they can flow. And in the same way that bringing the positive rod near the material caused separation of charge, holding something that is a conductor next to a Van de Graaff or anything with a charge will do the same thing. And so you can see that the charges in the nail, it still has the same number of them. Again, they can't leave unless you give them a pathway. You have to connect it to something. Okay, but there is polarization here, and that's why the distribution of charge is different. The one on the left is an insulator, the one on the right is a conductor, and you get polarization in that conductor. All right, so again, this stuff is temporary. When you bring the rod nearby, this is, by the way, one of the other simulations you saw, but it's similar to the first one. Now I have a negatively charged rod being brought near these beakers that each have a conductor on top, and there's two of them, and they're touching each other, and so they can flow back and forth between them, and that's exactly what happens. When this negative rod is brought nearby, because like charges repel and because electrons are capable of moving, the electrons will all move as far away as they can, which means they concentrate in this rod over here on the right-hand side of my screen. Please notice the protons are not moving because they can't, okay? But the electrons can. And so we get this temporary polarization. Whenever you move the charged body away, it goes back to normal again. Okay, but if you want to keep it permanent, you can induce a separation of charge, charging by induction, because you can do this, bring this body nearby, and then separate the two beakers. If you look at the bottom animation, that's exactly what they've done. Okay, and so if you cause this polarization and then you have these two objects that you can then separate, now because you had polarization first before you separated them, you end up with an object on the left-hand side that has a positive charge because it lost some of its electrons. They went into the other rod. And the one on the right-hand side has a bunch of extra electrons, and so it has a negative charge. That is charging by induction. It has a lot of steps. You have to polarize something first by bringing an object nearby without touching it, because if you touch it, that's conduction. We don't want that. Bring it nearby to get the separation, and then physically separate the objects while it's held nearby. This is going to result in one of your objects being negatively charged and one of your objects being positively charged. So if you were to look at these rods on top of the beakers after they are separated, the total number of electrons hasn't changed. Okay, you still have the same number, but they have shifted. And so now one of them might be a charge of positive 6 and the other one is negative 6 because you have transferred electrons from one to the other. That is charging by induction. Again, it takes a couple steps. There's another way to do it as well, and it's a different way that you saw in the simulation where you used the electroscope. So we talked about the electroscope yesterday. The electroscope also uses polarization because if you bring a charged object near the top of your electroscope, it causes the separation of charge. That's literally how it works. The one on top, that negative rod nearby, causes electrons to move far away from it, and that means they go into the leaves. Now my leaves are both negative and they flare outward, but I have a separation of charge. I have a positive top part and a negative bottom part. And the opposite's true here. If I bring a positive rod nearby, I still get the exact same motion of the leaves at the bottom, but now it's because both of the leaves are positive. We looked at this yesterday. So how do we keep the charges in the electroscope? How do we charge it? Okay, well, again, this is temporary. If you move it away, it goes right back. But the simulation also allowed you to touch it. Okay, again, if you did the simulation yourself, you could watch this happen, or maybe you watched the video where I was running the simulation. But you can ground the object or allow transfer of electrons between the ground and that material. And if you hold the negative object nearby when you do that, okay, then you can get the charges, like here they're flowing in to neutralize it, but you can also get the charges to flow out by giving them a pathway if you cause that polarization first. Okay, so again, we talked about grounding yesterday. Charge can be added or removed by grounding. Typically, we're talking about it allowing things to reach an equilibrium where it's uncharging, but you can actually use it to charge things as well if you're holding something nearby that also has a charge. Okay, and so again, if we ask this, why do the charges flow from the hand into the electroscope when it's touched? If we watch the animation when it starts over, which it's about to do, this electroscope is currently positively charged, and so again, when you ground it, typically we talked about this yesterday, this uncharging process, because it lacked electrons, it will steal them from you and from the ground, from the earth, until it reaches an equilibrium. Okay, but again, you can use this same induction to actually charge the electroscope in the first place. Again, it was something that you saw in the simulation. When you held the charged body nearby and touched it, that's how I got the positive electroscope in the first place. All right, so again, that's it for the types of charging. Charging by friction, charging by conduction, charging by induction. Those are the only three. To summarize, when you charge by friction, you take two neutral objects, you rub them together, and electrons transfer from one of them to the other one so that they have opposite charges. Again, we're not creating or destroying electrons, so if you're rubbing, like in the warm-up, steel and nylon, then you're going to have electrons move from the nylon to the steel, but if the nylon loses 12 electrons, the steel gains 12 electrons, and you end up with opposite charges. The same number of them, but opposite. Conduction, which we talked about yesterday, is when you touch a charged conductor, to something that is either neutral or has a different charge. And when we do that, we reach this electrostatic equilibrium. Our electrons flow until everything reaches a balance. After charging by conduction, your two objects have the same charge. Not just the same magnitude, but the same sign as well. Because if you touch a positively charged object to a neutral object, that neutral object will give some electrons away, and now both of them are missing some electrons. And we talked about the way to figure out the charge afterward yesterday. It was just some basic math. You can go back and look at those slides. But when you charge by friction, you get two opposite charges. When you charge by conduction, you get the same charge on both. Okay, and that is just by touching. And then today we talked about charging by induction, which happens when you bring a charged object near a neutral one to cause polarization, and then you separate them. Or maybe you bring a charged object near a neutral one to cause polarization, and then you touch that object, and that's going to cause electrons to either go into or out of the object, depending on what you brought nearby. And that can also cause a charge in that object that will stay there until it eventually reaches some equilibrium due to the humidity in the air or whatever else, or touching the ground. Okay, again, very common misconception that I just want to remind you of: you cannot transfer protons. So if I tell you a rod touches a sphere and afterward the rod obtains a positive charge, how did this happen? Please don't tell me protons transferred from the sphere to the rod, because no, they did not. Okay, if you have something that's a positive charge, it's not because it gained protons, it is because it lost electrons. Again, that is a very common misconception, so please make sure that you are not telling me that things are losing or gaining protons. It's only the electrons that are capable of moving. And again, ultimately, all of these interactions boil down to the same few general ideas and basic rules that we talked about on day one. Protons are positive, but they can't move. Electrons are negative, they can move, they will flow. Okay, in a conductor anyway. Opposites attract and like charges repel. That's the big one. If you can remember that, you can figure out any scenario. Electrons do repel one another, so they spread out until they reach some balance, some equilibrium. Materials lacking electrons will attract electrons or steal them from somewhere else. Okay, if you ground it especially. Until there's an equilibrium that is reached. Okay, so that is kind of the basics of this unit. It's a short unit. There's not a whole lot of stuff in here. For the rest of the period today, you're working on 1102.3 electrostatics problem set, which is basically a review of everything that we've done so far. It does have charging by induction on it, but it also has the other types of charging and those same basic ideas that we just went over. If you finish this early, which you likely will, I would strongly encourage you to start working on or continue working on your electric house planning sheet for the RA. Here's the deal, guys. There will not be a class day set aside to do that. Okay, so you can work on it today. When you take your quiz tomorrow, you can work on it after you take the quiz. Okay, but there's not a whole day of, hey, today's planning day. Okay, so you do need to find time to figure out what you're bringing, what everybody else is bringing, what parts of it you're doing, all of that, what style of house you're making. Those conversations, have them today or tomorrow, because tomorrow you have a quiz in My Open Math. You can do it afterward. You have a test on Monday, on paper, like normal. All right, guys, so go ahead and get to work. We have finished this whole unit, so now everything else is just a review. If you have questions for me, please let me know.